In this demonstration, we will look at debugging a USB 3 Linux device driver using Lauterbach's TRACE32 and the Synopsys Virtualizer development kit VDK for ARM Cortex. From a software developer standpoint, the VDK for ARM Cortex is very similar to ARM's well-known Versatile Express prototyping system. The VDK is able to run the exact same software stacks and provides connectivity to the same software development tools such as TRACE32. But instead of hardware, the VDK is a simulation model of the entire system, including all CPUs and the peripherals. It enables some key capabilities for hardware-dependent embedded software development, which we will learn about in this demonstration. Moreover, the VDK is extendable to support the latest CPU architectures such as ARM's big.LITTLE processing or peripherals such as USB 3, even before hardware is available. We will now start looking at the Linux boot on an ARM big.LITTLE processing CPU. A console terminal connected to the UART of the system shows the progress of the Linux boot. The VDK control and inspection cockpit allows to suspend and resume the simulation at any point in time. A virtual VGA console connects to the color LCD controller and the keyboard mouse interfaces and allows the user to interact with the platform. This is very much the same way you would also work with a hardware board. The full system can be suspended and the VDK provides visibility into all aspects of the hardware and the software. Here we are looking at the registers of the Cortex A15 CPU cluster. Beyond that, visibility into internal registers and even signals is provided by the VDK. For instance, here we are looking at the registers and signals of the Designware USB 3 subsystem. Now let's do some USB 3 Linux device driver debugging. Before we launch the USB 3 file system gadget, we will instruct the VDK to automatically load the symbols of the respective Linux kernel modules. We would like to suspend the system for USB 3 device driver debugging as soon as the cable is plugged in. The VDK allows us to put a watch point on the attach signal, which is raised as soon as the cable is plugged in. As soon as we plug in the cable, the entire system is suspended. As a next step, we are going to launch Lauterbach's TRACE32 debugger and connect it to the currently active Cortex A7 cluster. TRACE32 indicates that the CPU is currently handling an interrupt in the hypervisor mode task migration software layer. Embedded software debugging can now be fully controlled from TRACE32. With the VDK, debugging is non-intrusive. The tracing capabilities provided by TRACE32 are very helpful when it comes to integrating multiple software layers, such as here the interrupt going from the task migration software layer into the Linux kernel. Since we are interested in debugging the Linux device driver for the USB 3, we are going to set a breakpoint at the interrupt handler of the USB 3 device driver. Now let's investigate the trace of the interrupt coming from the hardware through the hypervisor into the Linux kernel. The Gantt chart provided by Lauterbach's TRACE32 enables full visibility into the processing of the interrupt through all the software layers. On top of tracing, Lauterbach's TRACE32 offers the ability to go back in time during debugging for a very efficient root cause analysis. After enabling the context trace system, we are able to debug the USB 3 device driver in reverse order. During back-in-time debugging, we of course have full visibility into, for instance, the call stack, the variables and the registers. Assuming we have completed the USB 3 device driver debugging, we now want to check the correct functionality of the USB 3 gadget. As soon as we let the system run, the Windows host PC recognizes the VDK as a USB 3 mass storage device. Using a regular Windows Explorer, we can copy a video file onto the gadget. Afterwards, we eject the mass storage device from the Windows host and subsequently unplug the virtual cable. Now we can play back the video that we have been just copying from the Windows host. As a final scenario for this demo, we would like to look at multicluster debugging. Here we are specifically highlighting the context switch from a Cortex A7 to the Cortex A15 CPU. As a first step, we will put a breakpoint in the switching function of the Cortex A7 cluster. We are triggering the switch to the Cortex A15 cluster by configuring the Linux Power Manager for high performance. Subsequently, the switch cluster breakpoint is hit and the Cortex A7 is preparing for power down, such as saving the entire context of the CPU. In the meanwhile, the Cortex A15 cluster is going through a warm reset and powering up by restoring the context. The embedded software on both CPU clusters can be debugged using two Lauterbach TRACE32 instances. The control of both debuggers is synchronized via a debug server that is integrated into the VDK. With that, I would like to finish this short demo showing how Lauterbach's TRACE32 can be used efficiently with a VDK as a target.